Okay, let's look at this tutorial 7 on magnetic interactions. I'm going to share my screen and what you're seeing right now is a little swing made of wire. And we're going to connect that to a battery and then hold a magnet underneath it and see which way that swing uh, is pushed. So let's go to the tutorial handout. Um, Here's a picture of the apparatus. There's the swing, and we're going to hook that to this battery, remembering that the knob on a battery is the positive end, and this is the negative end. And so that means that the conventional current is going to leave the positive and be going through this wire to the right. Okay. So um, if we want to sketch the field lines representing the magnetic field of the bar magnet, um, we're going to have them coming out of the north and into the south. And we found that out here, they circled back around. And we're going to keep on finding that over and over again, that magnetic field lines um, always close on themselves. They don't just end someplace, they always close on themselves to make a complete loop. Now, the magnetic field that is going to affect the wire, the current in the wire, remember the current in the wire is going this way, that's going to be the B field right next to that North Pole, which is going to be away from the north. And so if I want to predict the direction of the force um, by the magnet when the circuit is complete, when I connect this uh, clip to that battery, I would use right-hand rule number 1. Well, that's the right-hand rule for force, and it's the only right-hand rule for force. Now, before the end of this tutorial, we're going to have 3 right-hand rules, and so I just want to make clear that this is the only one that gives us a force, a push, or a pull. Now, to do this right-hand rule, we first of all turn the page so that I can reach in the direction of the current, the flow, the movement, without hurting myself. And then I've got to turn my wrist so that I can wave in the direction of the B field. And that's going to force my thumb in the direction of the force. And you see that my thumb is pointing up towards the camera. And so that means the force is going to be um, the magnetic force is going to be out of the page, out of the page. And we're now going to check our prediction. Let's make a lot of predictions and then we'll come back and check all of them. What if I turn the magnet so the south pole is near the wire? Well, now I'm going to have the current going to the right, and I'm going to have a south pole here. Well, the field due to a south pole uh, is towards the South Pole. And so now if I do my right-hand rule number 1, I reach in the direction of the flow, the motion, and I turn my wrist so I can wave in the direction of the B field. And now my magnetic force is going to be into the page. If I reverse the leads to the battery, well, now the current is flowing this way instead of the other way. If I were to have a north pole here, such that the B field was like that, well, I expect to get the opposite result of what I got in the first experiment. And sure enough, if I reach in the direction of the flow, turn my wrist so I can wave in the direction of the B field, my thumb is pointing into the page. And so I get a magnetic force into the page. And if I did that same thing with a south pole, I would get a magnetic force. These are vectors that would be out of the page. So those are our predictions. What if the north pole of the magnet is held near the wire, but the battery is not connected? I predict we'll get nothing. If the north pole of the magnet is held closer to the wire, further from the wire, bigger force when magnet is closer. Well, why do I predict that? Well, it's because these magnetic field lines, due to the bar magnet, they spread out. Once they leave the pole, they spread out. And so that means my magnetic field gets weaker the further I am away from that pole. And your experience with magnets has told you that that's true, that the strongest field is going to be right here next to the pole. Now, the last one is the magnet is turned parallel so that it is turned sideways so that it's parallel to the wire. So let's go back to the original current going this way. If I have my magnet like this, well, in that case, the magnetic field is going to be parallel to the current or anti-parallel here. And so I'm not going to get any effect due to this field here. Remember, it's only when the charged particles try to cross the field lines that we have a force. Now, there will be a force at this end of the wire where we're going like that. And we found that with the north magnetic field going up, we found that we got a force out of the page. And so I predict that we would, right at the end, get a weak force out of the page. And over here, we would get a weak force into the page. And so the wire swing is just going to kind of torque a little bit. It's just going to twist. Now, we want to ignore this hint. This hint was meant for people in the calculus-based physics class. So we made some predictions a while ago, and we predicted that when I held the North Pole near this wire, with the conventional current running to my right, and that would be away from the camera there, that the swing would come towards me, which from this angle would be, it would swing out to the right. Well, let's just check that real quick. I've got the North Pole of this bar magnet here. I'm going to hold it right underneath the swing, and I'm going to connect the circuit right now. And sure enough, it goes to the right. Let me stop that. So the second prediction we made was that if we held the South Pole next to that wire, it would swing the other way or away from me. And so let's do that. And I'm going to close the switch right now, and sure enough, it swung away from me. Okay. Well, we also predicted that if we turn this battery around so that the positive end was over here, that would drive conventional current to my left or towards the camera, and we predicted that that would reverse the results that we saw before. So I'm going to close the switch. I'm going to bring the North Pole up, and sure enough, it deflects away from me. And now if I bring the South Pole up, it deflects towards me, as predicted. Okay. Now, we also predicted that if we disconnected the battery, nothing was going to happen, and that's just an easy prediction to check. We also predicted that if we put the magnet closer, we would get a bigger effect, and we can test that by having the magnet further, and you know what's going to happen there. So let's stop there. Okay, that was kind of small. Let's do it on a bigger scale here. If I have a conventional current traveling down this wire and across to our right, in a magnetic field that's pointing out of the north and into the south, so the magnetic field would be down in this case, let's predict what we expect this wire to do, how we expect it to be pushed. Well, if we use the right-hand rule, we reach with our right hand in the direction of the flow of conventional current. And then we turn our wrist so that we can wave our hand in the direction of the B field, the magnetic field. Our thumb is going to tell us the direction of the force on the wire, and this is predicting that it will be pushed in. So let's test that. I'm going to close the switch now. I think that was in. Yeah, that looked in. Okay, so now I'm going to switch the leads so that the conventional current is going through the wire the opposite way. Okay, so now the conventional current is flowing to our left, and the field is still going from the North Pole to the South Pole or down. And so now my thumb is pointing out, and we expect that swing to swing out. I'm closing the switch now. Whoa, yeah, that's all sorts of out. Okay. Now we could turn the magnet around and do it again, but we know what the results will be, and it's kind of a pain to get that thing out of the cradle. So we're going to splice it there. Now, if we hold a compass near a current carrying wire, we find, just as Ørsted did in his famous experiment, that the compass needle will be affected by that current. And what we're going to find is that if I have current traveling to the right, conventional current, if I put the compass needle down here, my North Pole is going to be into the page, And up here, the North Pole will be out of the page. And what we find is the same thing uh, that Ørsted found, and that is if we look from this direction, if that's our eyeball looking down on the current like that, what we're going to find is that the current will look like it's coming towards us, and the magnetic field caused by that current is going to be given by right-hand rule number 2, where we use the straight part of our right hand to represent that current coming up towards us, and the curved part of our hand, the fingers, indicate the direction of the magnetic field. Now, a compass lines up with the magnetic field, so if I put a compass here, the red arrow would point that way. If I put that compass here, the red arrow would point that way. If I put it here, whoops, let's put it here. The red arrow would point that way. If I put it here, the red arrow would point that way. So it makes circles around uh, the wire that's carrying the current. Now, we have just finished that. We finished that part there. Okay, let's talk about this uh, current loop, and then we'll talk about solenoids, which is just a bunch of current loops. We take a wire, we form it into a loop, and we twist the leads together. The sides of the loop are labeled A, B, C, and D, and the direction of the current is shown, and by that we mean conventional current. And so it comes down wire A and across B and up C and across D. Now, we're going to use the convention that this symbol is out of the page, and this is into the page over here. So here we're looking at a side view from this side here. That's our eyeball. And so here the current would be going away from us because our eyeball sees it going away. And here it would be coming towards us because this one's coming towards our, that's not much of an eyeball, is it? Okay. You probably have to use your imagination more than you wanted to. There. Okay. Um, we want to sketch the magnetic field lines for the loop. And what we're going to use is right-hand rule number 2. And you remember right-hand rule number 2, we use the straight part of our right hand to represent the current, and the curved part of our right hand represents the magnetic field lines. So first of all, they ask us, why is it reasonable to ignore the effects of the magnetic field from the wire leads? Well, one's carrying current this way and one's carrying current this way, and they cancel out. So we just have to worry about these 4 segments here. If I look at segment A, I'm going to turn my page around so that I can put my thumb in the direction of the current. And now you see that if I wrap my fingers around, my fingers are coming out of the page on the inside of that loop, and they're going into the page outside the loop. So I'm going to draw the magnetic field like this. And remember, that's magnetic field. Now, if I do this current here, again, by right-hand rule number 2, the field lines are coming out of the page in the inside and into the page on the outside. And so I would draw that like that. If I do that again with C, it's out of the page in here, into the page over there. And again, if I do that with this one here, it's out of the page there and into the page there. Now, we want to look at this on the side view. And so if I am going to rotate this by 90 degrees about this axis right here, such that wire C comes closer to me and wire A goes further away from me. Let's see what we get. So this represents that wire loop that we were talking about just a moment ago. This is the corner where the two leads came in, and we don't have to worry about the magnetic field due to these two leads because one has current going one way and one has current going the other way, and they cancel out. So remember, the current was going down this wire, over here, up here, and over there. And what we found was that for each of these cases, each of these wires rather, the magnetic field came out towards us in the middle and then went back away from us outside of the loop. And so if I look at this wire, by right-hand rule number 2, that's going to be towards you in the middle and away from you outside. And down here, it would be towards you in the middle, away from you outside. And up here, it would be towards you in the middle, away from you outside. So what we're asked to do in the tutorial is look on a side view where we bring this side that doesn't have the leads towards us. Well, let me represent the magnetic field that's coming out towards us in the middle with my hand. Think of those as field lines. And now if I turn this to the side so that we're seeing a side view, you see that all the field lines are coming through the middle of the loop and then wrapping back around and coming the other way. So coming through the middle and wrapping around the other way. And we're going to talk about that back at the tutorial. Okay, from that discussion there, it looks like those field lines are going to be coming through that loop from right to left, and then they're going to wrap around outside the loop and come back in. Okay, outside and back in. And it turns out that this is a common feature with all magnetic field lines. They always wrap around and close on themselves. They don't just stop or start. They always make a complete loop. Now, if we consider the magnetic field of a bar magnet, well, it looks pretty much the same. If I had a bar magnet here instead of a loop, with a north pole here and a south pole there, the magnetic field lines would come out of the north, wrap around, and come into the south. Out of the north, wrap around, come into the south. And so we see that a wire loop acts like a really short bar magnet. And I can identify a north and a south pole. And that's just by looking at which side of the loop the field lines are coming out of, because the field lines come out of the north. And now we can devise a rule by which we can use our right hand, oh goody, another right hand rule, to identify the magnetic poles of a loop. Well, if in right hand rule number 2, I was using the straight part of my hand to represent the current, and the curved part of my hand was representing the magnetic field. Well, with a current loop, let's use the curved part of my hand to represent the current. Well, it goes away from me at the top and towards me at the bottom. So I curl my fingers away from me at the top and towards me at the bottom. And looky here, my thumb, the straight part of my hand, is pointing in the direction that the magnetic field is pointing through the loop. Or, equivalently, it's showing me the side of the loop that is the North Pole. Okay, so we're going to call that right hand rule number 3. So right hand rule number 2 gives the B field for a straight wire carrying current. And right hand rule number 3 gives the B field for a current loop. Okay. Now, if we deal with current loops, and we will in homework and in the exam, um, we find that it's much, much easier if we replace that current loop with the equivalent bar magnet and then pretend we're in the second grade. Because at that point, in the second grade, we knew how bar magnets were going to work when they were next to each other. So let's see if we can make that happen here. So if we're told to draw vectors to show the magnetic force on each side of the loop, let's remember that magnetic field comes out of the north like that. So if I use my right hand rule and reach in the direction out of the page for the current, and then swing my hand in the direction of the B field, I get a force that way. If I do the same thing on this end, I get a force that way. And you see that's going to try to make that loop rotate a little bit, um, about 30 degrees, and then it'll stop. But it'll rotate counterclockwise. Now, if I look at the net effect of those magnetic forces, even though the forces are probably going to cancel each other, the net effect is that the torque will not be zero and it will rotate the loop. Now, if I use my right hand rule number 3 to replace that loop with a bar magnet that goes right through the loop, and my right hand rule number 3 tells me that the north side of that bar magnet is going to be there and the south pole will be there. Well, now go back to the second grade and ask yourself, if I had a bar magnet that was free to swivel about the center, and I had a south pole here, which way would this thing rotate? Would it go clockwise or counterclockwise? Equivalently, you could think of this bar magnet as a little compass needle, where the north-seeking pole has the arrowhead. And sure enough, the south pole of that compass needle would be attracted to this north pole, and it would rotate so that it was pointing like that. Now, if we do the same thing over here, by doing our right hand rule number 3 and replacing this with a bar magnet, this time our right hand rule number 3 tells us that this is the North Pole and this is the South Pole. Um, and so now this thing is going to rotate the other way until it ends up like this. Okay. And this is there an orientation for which there is no net torque on the loop? Yeah, this is it right here. That's it right there. Okay. Because now I can think of the magnetic force on this part of the loop pointing that way, and the magnetic force on this part of the loop pointing that way. And that's going to give me zero torque. Are our results consistent with regarding the loop as a small magnet? Yes, indeed. If here we had the magnetic force. Okay. A solenoid is an arrangement of many current loops placed together as shown. And the current through each loop is the same and it is in the direction shown. So these are loops where the current's going into the page at the bottom, out of the page at the top, into the page at the bottom, out of the page at the top. So this is wrapped around this tube. We've got some plastic tube that we've wrapped wire around and then we hooked it to a battery. Now at each of the labeled points, draw a vector to indicate the direction and magnitude of the magnetic field. Well, using superposition, we can say that the magnetic field in here is going to be this way. And here it's going to be this way. Here it's going to be this way. Here it's going to be this way. Now, how am I getting these answers? Well, um, to be perfectly frank, uh, I'm getting these answers quickly because I'm thinking of this solenoid as a bar magnet. If a single loop can be thought of as a short bar magnet, a whole bunch of loops in a solenoid can be thought of as a long bar magnet with a north pole and a south pole. And I know that the field lines come out of the north, wrap around, and go into the south. Now, if I wanted to actually use what we learned about a single loop, I could do superposition. At this point A, each one of these loops is giving me a contribution to the right. And so when I add those all up, I get something to the right. Likewise, since this is also on the symmetry axis at point B, every one of these loops is going to give me a contribution to the right. And when I add those up, I'm going to get something to the right. Well, if I look at point D, that's an interesting one. If I look at the contribution due to this loop, I get something to the right. If I look at the contribution over here, I'm going to get something that is uh, that way. And if I look at a similar contribution due to something over here, I'm going to get something that is um, let's see, that way. But those would be very, very small contributions. And so you see that I'm going to get, when I add them all up, I'm going to get something that is this way, but very, very weak, very weak. How does the field of the solenoid at A to E compare with that of a bar magnet, both inside and outside. It's the same for reasons we'll talk about in lecture. Which end of the solenoid corresponds to a north pole? That would be that end and that end. And how would the magnetic field at any point within the solenoid be affected by the following changes? Well, we don't have enough math background to answer these questions, so we're just going to skip those and call this the end of the tutorial.